Good morning, everybody. It's a pleasure for me to introduce to you the next speaker, and the next talk or lecture is in fact the Emanator Lecture. The Emanator Lecture is a lecture series of the German Mathematical Society. It takes place on its annual meetings for a couple of years now. It has started a few years ago on the annual meeting the German Math Society held in Erlangen, which is the hometown of Emanator. As you know, she was a mathematician working some 100 years ago or so. Now, the Emanator Lecture is meant to honor an excellent speaker, and also it is meant to support women in mathematics at large. So as the prominent speaker goes, I'm very happy that we have a very distinguished speaker today here to deliver the Emanator Lecture, Barbara Wohlmuth from the TU Munich, Technische Universität München. Let me say a few words about Professor Wohlmuth. She's, as you will see from her talk, or you can see it already from her title, she's a numerical analyst and also working in scientific computing. And she's originally from Munich and grew up there and studied in Munich. And then she went around the world, so to say. About 14 years ago, she was appointed professor to be a professor in Stuttgart, and 4 years ago she then changed to Munich, where she is since. And she was awarded several prizes. The most prominent one is the Leibniz Prize of which is the highest prize of the German Science Foundation. And so I'm very happy that now this distinguished speaker will present her work to us. The stage is yours.
Is it already on?
Sounds like that.
Okay, so I'm very honored to be here today, and I would like to thank the organizers for this perfect meeting here. It was very smooth so far, very interesting and challenging discussions during the breaks. So as already mentioned, I would like to bring you some ideas from numerics, but also from the interaction of numerics with different disciplines, such as engineering on one side and computer science on the other side. So the talk is structured as follows. First of all, I would like to show you just two simple model equations where model reduction techniques coming from mathematics can help us to go a step forward to what we can do by simulations nowadays. And only in the second part, I will focus more on some numerical schemes, where new numerical schemes can help us to improve the efficiency of simulation algorithms. And finally, in the last minutes, I will just pose some new challenges for modern algorithms coming with a large development in hardware and the possibilities coming with this. So to start with, we have in daily life many applications which involve multiphysics. What is multiphysics? Basically, quite often you find it in engineering applications, but also in flow problems such as porous media. Porous media appear in very different fields, like medicine, so the soft tissues in your body can be modeled by equations from porous media. But also in the soil, in evaporation processes can be modeled by porous media equations. And finally, you have the coupling between the free flow, for example, the air flow, and the soil properties, and you have evaporation processes between these two subdomains. Another example, very important one, Elasta Acoustics. So all of you have been most likely spending nights in hotels. It was not able for you to sleep because of the noise. So noise is a huge problem nowadays, and the interaction between mechanics, here you have it in the positive form of a loudspeaker. Also music is related to this. And the interaction between the mechanical equations of this part in the loudspeaker, such as elasticity equations, and the acoustics are examples for simulation techniques in multiphysics applications. And finally, we are going to a volume-coupled applications coming from geophysics. Here you have flow problems again, but the interaction of the flow with temperature, so with energy balance equations, and in the non-isothermal field, in contrast to simple Stokes problems, you have not only the velocity and the pressure, but also you have to simulate and model the temperature. And finally, and this is an example which I will start with, are networks. So networks can be root networks of plants, but also blood vessels can be modeled as networks. And what is the characteristic of a network here? You have basically a thin structure which can be represented quite often as a one-dimensional, or at the endpoints here, even as a zero-dimensional PDE or ODE model. But then you have, of course, also the interaction with the soil, with the so-called matrix. And this is still a three-dimensional PDE. So, coupling 0D, 1D, 3D in such a setting, you see the quite complex network with bifurcation points, with the large parts, but also with the thinner vessels, with ending vessels. And finally, you would like to simulate the effect of a stenosis. What is a stenosis? It's basically narrowing. And if it's too large, then it absolutely blocks the blood flow. And of course, this is a work which cannot be only done by mathematics. Here you need exactly the impact of people in the medicine departments. So at the end of the day, you end up with a 1D model in all these parts of the human body, except the lower part where you apply a 3D model, and here you have a zoom of this 1D 3D coupling, whereas in this zoom here, all these parts of the vessels are ignored. But here again, you work with 1D transport equations, sometimes highly nonlinear, which come from averaging of Navier Stokes equations, basically. And for the smaller parts, you work with linearized models. And at the out part here, you work with 0D models involving also some automatic, adaptive, controlled resistance model. Otherwise, it would just flow out. So what is the flow rate? So the flow rate below the stenosis, you see the more the stenosis is severe, going from no stenosis at all, a healthy vessel, to an absolutely blocked one, the flow rate drops down to zero. This is what you would also expect, of course, but the consequences for the human body are dramatic, because this is now the oxygen concentration in the neighborhood, in the tissue of your body. And again, if you have a healthy vessel, there's absolutely no damage effect which can be seen. The oxygen concentration is quite uniformly distributed. But then you consider the stenosis, and if it's fully blocked, then there's no oxygen contribution in the lower part of your leg. And the effects are, of course, dramatic. So, what do we have to understand from this type of easy model? We have to understand how the influence of a distributional source on the right-hand side of a PDE, which is posed in a three-dimensional domain, influence the regularity of the solution, but also influence the choice of our numerical schemes. Because in all these examples, we are not in the situation to find analytically a solution. We depend on accurate and reliable numerical schemes. So this is, again, a sketch of what's going on. In reality, if you go to a fine scale, everything is a three-dimensional PDE model. But you do model reduction in the sense that these small vessels are modeled by 1D PDEs. And then you have the bifurcation points where you have to take principles as steering and interconnecting into account, and you have to have the endpoints which are modeled as zero-dimensional, so ODE equations. But not only this model reduction introduces singularities into the solution, because the right-hand side is, for example, only a point source or a line source term, but also corners in coupled schemes introduce singularities. And the question is, which singularity is more severe? Well, from the analytical point of view, of course, the first one, because the regularity of the solution is lower than compared to the second one. Whereas from the numerical point of view, you should be more worried about the second one, because the second one in numerical schemes gives you pollution effects. What does it mean, a pollution effect? A pollution effect is the following one. You obtain a numerical solution, for example, with a finite element or finite difference method, and this solution is not as good as it could be. And by could be, I mean it's not in the same order of magnitude in the accuracy as if you would have the best approximation of the solution. But the best approximation of the solution is not accessible for you during your numerical scheme. So pollution is something where you put a lot of effort to get your discrete solution, but it's not as good as you hope for. So this is not a good thing to do. And the corner singularities are well known for having exactly pollution effects, for example, in the L2 norm or in eigenvalue computations or in stress intensity factors. So are corners really as important? Well, corner singularities are everywhere. I hope that after a couple of days of the conference, you recognize this logo. You see that if we model it by a simplified domain, we have two different interior angles. One is a characteristic angle of an L-shaped domain, here marked in green, and the other one is also quite close to an L-shaped domain. And at all these 8 corners, you expect solutions with singularities. So what can be done in case of numerical methods? There's a huge amount of references on how to deal with singularities in domains. The first one is basically very popular in physics. You enrich your approximation space by exactly singular function. So you just add. But unfortunately, the singular function is singular, and therefore it's not so easy to integrate it numerically, to have a stiffness matrix which is sparse. So all these effects, which are quite computational expensive, come in. And an alternative way is to use a graded mesh. So what is a graded mesh? So numerics is always based on some discretization, meaning that you have to decompose your domain into sub-elements. It might be triangles, it might be quads, it can be mixed, it can be combined. And a graded mesh, with respect to a corner singularity point, so for example, if you have here this corner singularity, what is a graded mesh? Well, the mesh close to here is very, very fine, whereas the mesh here is quite coarse. This helps you to improve the accuracy, but you already see that it brings in many, many more degrees of freedom here close to the corner point. Again, computational expensive. So the first 2 approaches work very nicely. They work. You can prove convergence. You can prove that they get rid of the pollution effects, but they cost you something, and they change the data structure of what you have. So this is not as nice to work with. But then there's a very old idea coming from the community of finite differences saying, well, whatever we do here, this is just a simplified mathematical model. We are not interested in the solution at that point. What we are interested in are more global quantities, like eigenvalues, like stress intensity factors, like outflow quantities. So they are not directly associated with the singularity. So we would like to modify our scheme. And the observation was that energy which is in the system hidden by the partial differential equation, because at the end it can be recasted as an energy minimization problem, this has to be corrected. And this observation is so trivial that it's even not a homework, it's even not a class work. So we have the Laplace operator. We consider this. We set homogeneous Dirichlet boundary condition for simplicity of notation. We go to the weak formulation. We are looking for an element in H01 such that for all test functions we have this equality. And this defines our bilinear form A. Of course, it's symmetric and positive definite on the space we consider. Okay, what does the numerical scheme? A finite element approximation mimics this property, but not in infinite dimensional space, but just something in a finite dimensional space. This dimension is now finite, associated with the number of elements we have here. The more elements you have, the higher the dimension is here. And if the mesh size, so the maximal diameter here, tends to 0, then this space is tending or is dense in the H01 space. So, and now you just can subtract these two lines, provided that the V is in this space, and this is called a conforming approach, because for a conforming approach we require that the VH is a subspace of the H01. Now, subtracting these two lines gives us something very simple, and we put in the first line for V equal U, and for the second line we put in for V equal UH. What we find is that this is equal F times U minus UH. And then, very simple bounds. We have this upper bound here, where alpha is now a parameter and provides you the weight in the L2 norm. So you're working with weighted L2 norms. So this is trivial what we have here. We can even make it like this. Okay, and this tells you something very interesting. Pollution can be seen here in this norm. So if you would like to get rid of the pollution, you would like that this norm converges better as it is in a standard scheme. But what does this mean? This means that this quantity, which is a scalar quantity, has to be corrected, has to be modified. And this is exactly the idea of energy-corrected finite elements. They don't try to mimic the singular function. They don't try to approximate something better, but they only try to get the energy correct. And this is the idea, to modify the scheme such that the energy is corrected. And in fact, one can show that this is not only a necessary, but also a sufficient condition for the fact that no pollution effects occur. So, correcting the energy will do the job. Now I have these three hands. And this is also what the theorem states, is that there exists a parameter, a unique parameter, such that you can modify your bilinear form in a very simple way, and the pollution effect is gone because now you have best approximation property from what you can expect from linear finite elements. Linear finite elements cannot be better than a quadratic convergence order, regardless of the singularity in the solution. So how is this modification done? Well, for engineers, this would be not surprising because they just modify the stiffness of the membrane here in a very small neighborhood around the corner. This is exactly hidden in this formula in the middle of this page. You correct, you modify the bilinear form, you take the original one, and then you subtract this one, and this one is defined as the original one, but just restricted on a small subdomain of the domain, on this omega L, and the omega L compromises all elements of your mesh which are directly attached to the corner. So that's the story. And this is a nice theoretical result in the sense there exists a unique gamma such that if you have it, you can do good numerics. But for numerical simulations, the method is easy to implement provided you have this gamma infinity. Without this gamma infinity, the method is worthless. You need this gamma infinity. So the question is, how do we get it theoretically, and then, and this is something I will not answer here, how do we get it numerically? Theoretically, the answer is to some extent easy because you can define the energy correction function which just subtracts from the continuous energy the discrete energy with respect to this modified bilinear form. And now you're looking for the root of this. Because, as we see, this is the energy, and we would like to try to make this as small as possible, and this is meaning that we are looking for the root. So we are just looking for the root of this energy function, and it can be shown that this is a monotone function, and it has exactly one root, and moreover this root depends on the singular function, so it depends on this angle here, so it's different if we have a domain like this or a slit domain, and it depends also on the mesh size. So for each mesh size, we do get a different one. We get these gamma L stars as the root of these energy correction functions, but they converge. They converge to this gamma infinity, and this time the proof is not a class work. Okay, what is the effect? Very simple domain with several slits. Standard finite elements. You have a quite reduced convergence rate. You're not going for 1, you would like to see a 2. So instead of h squared, we have a convergence rate of order h, coming from the fact that the analytical solution is not in h2, but basically in h1.5. Now the energy corrected finite elements, the convergence rate is very close to 2, and the same accuracy is obtained on a much, much coarser mesh, because what you see here, the lines of this table indicate mesh refinement. You start with a coarse mesh, for example, like this, and then from one row to the next one, you decompose each element into 4 sub-elements. And you do this in each step from each row to row, you do this decomposition. And of course you improve the solution, but the gain in accuracy is with the energy corrected finite elements much, much faster. So you have really, by this simple trick, highly improved the convergence rate. And what about computational complexity? I mean, as soon as you have the gamma, there's almost nothing to do. It's just a few lines, like 5 lines in your stiffness matrix, in your huge matrix with a couple of 100,000 lines, you have to change 5 lines. That's very simple from the point of data structure. So going back to the first example we had, it was this star shape. We do corrections at each of these corners, these interior 4s, but also at each of these 4 corners. And this time we are not going for a weighted L2 norm, but we are going for eigenvalue computations. And also for the eigenvalue computations, the convergence rates are highly improved. So pollution effects can be compensated by a smart numerical scheme which does not bring computational effort. But the examples we have seen so far had been mainly designed to do a reduction first with the idea of having a much smaller system which can be still solved on a laptop or on a small cluster with only a few cores. But there are, of course, many other examples where this is not possible. If you have not a million, but a billion of unknowns in your system, it's not sufficient to do the thing on your laptop. You need different machines, and for these different machines, these supercomputers, you also need different algorithms. And this is now the trick, how to make algorithms, mathematical sound algorithms running on these machines. First of all, they should be as simple as possible. Secondly, you should never satisfied with your timed solution. You should always ask, why is it not better? And then you should make a performance model, seeing really how powerful is your node performance in your computer. What is the memory bandwidth? And then check your algorithm again, count the flops, count the communication, and you will see you have a huge gap in between. If you do this computation, you would expect that your algorithm is 10,000 times faster than it is actually. So now you have to push it hard to the limit and try to see where you lose it. And quite often you lose it in communication, because communication is something which classically is ignored if you design algorithms. You count only for the flops, but not for the communications. And then make it fast. And to do so, I am showing you a different example coming from geophysics. Basically, you have the Stokes equations here. So Stokes equation is a partial differential equations where you have second order terms for the velocity. The velocity is a vectorial quantity. The sigma is the stress tensor. The stress tensor is defined in terms of the strain tensor plus some additional components coming from the pressure. So you have here the formal definition of the stress tensor where the viscosity enters, and the viscosity in general is an unknown depending also on the temperature but also on the radius in the example we are considering. In addition to it, you have the energy balance equations where basically again you have the feedback, you have the coupling between the two models, because the viscosity and the velocity, they enter again into the energy equation. The velocity drives the convection into this model. If you simplify it, if you go to a simplified Earth mantle convection in a nutshell, then at the end of the day you have to solve the classical Stokes with a temperature on the right-hand side, and then you have to solve the temperature equation, which is of parabolic nature, where the velocity enters as a magnitude here in front of the gradient of the temperature. You can decouple it in a time-dependent scheme. You do time integration by a method here, and you just use an explicit form for handling the velocity. And if you do so, then these two systems decouple, and because in the first step you solve for the temperature, and in the second step you enter the already pre-computed temperature into the velocity equation. So basically, where is the computational effort? The computational effort is in this system here, because it's not an elliptic system. In the classical sense, you end up with a huge matrix which has positive and negative eigenvalues. And unfortunately, many of these extremely fast iterative solvers do not work for this class of matrices. So we are using the simplest approach. And of course the question is, why are we not using some fancy discretization schemes? Well, because the simplest approach is at the end of the day the fastest one, because it has a very minimized data structure, and therefore we are not losing too much on overhead in communication. What are the advantages of linear finite elements? Well, they show superconvergence, quite recently proved by the group of Tobisker. They can handle systems with a billion of unknowns because the sparsity of the system is extremely small. It's quite close to finite differences. What are the commonly mentioned disadvantages? Well, disadvantages are it's not locally mass conservative. And this is a big physical problem, because then you bring in spurious mass, you have source or sink terms in your simulation domain. They are not stable. I mean, come on, what can we do with a method which is not stable? And they are poorly suitable for convection-dominated problems. But again, we are facing this type of problem. So we have to work with these disadvantages, and before one can seriously consider this type of element for the application we have in mind, we have to overcome these disadvantages. We have to find the remedies for these 3 points. Well, the first one is fortunately already solved for us by the literature. There's a huge amount, like apple pie recipes. Each group has its own favorite stabilization technique, so you can pick whatever your personal favorite is. But the other 2 ones are more tricky. And this is, I would like to show how to handle the first one. What is mass conservation? Well, in a strong way, we would like to have that we have pointwise that the divergence of our numerical approximation is equal to 0. This is basically the strong mass conservation here. But what we have from our scheme is that we have it only in a weak form, tested with some test function, which might be quite different depending. And even worse, because of stabilization, quite often you have extra terms in here which bring into the pressure. So you have, instead of the strong form, you have a weak form. And if you assume for the moment that this C part is equal to 0, then at least you see a correlation between these two. But it's of course not exactly the same. So how can we get from weak to strong conservation? This is by assuming a 2-level stabilization, meaning that if we put in here C which lives on the coarser mesh, that this term is equal to 0. It's not always 0, but if you go to the coarser mesh, it is 0. So we have a hierarchy of 2 meshes. This is the fine one. This is the coarse one. So that's the first step. And because the C now is equal to 0, we have this line here. Now we associate with our primal mesh, which is associated with triangles, a so-called dual mesh. How's the dual mesh designed? Well, you just take the centers of the edges and connect all of them with the centers of the triangles. This gives you the dual mesh. And the primal mesh is nested. This is the fine one in black. This is the coarse one. But the dual mesh is not nested. As you can see here on the right, the red dual element is not a union of blue boxes. The blue boxes, there is one in the interior, but the other ones here are half out, half in. This is the tricky part of this dual mesh. In 3D, the situation is basically exactly the same, but if you give it to a student to implement it, he will not agree with you. For him, it will be not the same, because the implementation, of course, is much more technically involved, but from the structure, from the principle, it is the same. Again, you connect the centers of the different primitives, such as edges, faces, and elements. Okay, now we have this dual mesh. What do? We take the flux. The flux is basically the velocity in normal direction through the edges. And we take this, what we have from our velocity, and we correct it. We add something or subtract something. And this correction is defined as a difference, and it exactly corrects the difference in the mass loss or mass gain. And it's an easy integral because it's just the integral of this half box which is outside, and then you take the integral on the boundary of this half box which is inside, and you take the difference. This is not very handy to implement it because then you need all these sub-edges, you have to find the normals, and so on. Much more handy is the following way to see it. You apply integration by part, play it back to a volume integral term, and then you exploit the fact that the divergence of UH is piecewise per triangle constant, and then you see that these two contributions coming from this and this triangle cancels out, and this triangle, this shape here, is just a third in 2D of this green triangle. And this gives you just a scaling factor, that's it. So, you see here numerically the influence. On the left, there's no correction at all. On the right, you have implemented additionally this correction, and a constant is now transported to a constant, whereas here, a constant is, well, after a couple of time steps, not a constant anymore. And that's, of course, bad because it's not conservative at all. And this is a circulation of two species. It's a transport problem. And you have here the perfect mixturing process, whereas here, everything spurious oscillation from numerics come into play. So, now we have overcome all these problems with lowest order, equal order discretization schemes. Now we would like to run it really on the big machines. So what are the crucial ingredients? First of all, don't assemble the matrix. Even if you have a sparse matrix format, you have to store it. So as everything is matrix-free, everything is computed on the fly. Then go to a hierarchy of meshes and exploit in the solver multigrid schemes, which are known to be optimal iterative solvers. Then reduce the data structure and the communication as much as you can. Because if you think about a PDE, you have a domain partitioning, then directly the points here, the degrees of freedom, do not interact with the points here. They interact with the points here, but only by these interfaces. And this is something you should implement in your data structure and separate volume and interfaces in the data structure. And then finally, we would like to get rid of this positive-negative eigenvalues. We go to a show complement formulation, which does static condensation formally of the velocity, but of course never implements the inverse of A. I mean, this would really, really kill you. So, going back to a fairy tale, I tried to tell you that it's trivial, but now we will see that it's not as trivial, and in high-performance computing you have two measures of scalability. You have strong and you have weak scalability. And quite often, to some people not so much in the field, they don't recall which one is which one. So, strong scalability. We start with the fairy tale of Cinderella. She would like to go to the ball, but she gets by her stepmother a job to do before. And she cannot manage to do the job by her own. It's too big. But she's getting the help of two dogs. And when the time is over, only half of the job is done. So again, no chance to go. So she's bringing in more dogs. With the help of 4 dogs, when the time is over, the job is done. But she's still not really dressed nicely up, so she cannot leave for the ball. And only when really an army of dogs comes in, they are so fast that there's plenty of time left to dress up and to leave for the ball. So this is strong scaling. The amount of work you have is still the same, but you bring in more computing power. And of course, if you double the computing power, you would like to have that your simulation code runs twice as fast. But you can already see from this picture to here that it will most likely not work out as you hoped for. Why not? Well, if you have this huge army of doves, they can never, all of them, work at the same time in parallel on this job. They will interact, they will start to fight, and they will slow down the process. And that's exactly the same what happens on supercomputers. You have this huge army of processors, 100,000 up to even 1 million, and now you have the job to do to distribute, and the communication should be easy and smooth. And that's not so easy. So here we have some examples on 2 different German supercomputers. Why 2? Why it's not sufficient to test it on 1? Because they're of different types. How can you increase computing power? Well, you can make the processor faster, stronger. You can go for a high node performance, or you can just put in many more processors. And these are the 2 different strategies. SuperMOOC has a relatively few number of cores, but a very high node performance of each compute core, whereas Queen has many, many more cores, but the performance of each core is substantially smaller than in Munich. And the scalability rate is here. It goes down, but it stays below 50%, which is regarded as an excellent result. So this was strong scalability. Now we have to go to weak scalability. What is weak scalability? Going back to our fairy tale, I mean, Cinderella is not as lucky. She has a mean stepmother. So when she realized that she will manage the job to do and leave for the ball, well, she just increases the workload. And this is what you measure with weak scalability. You bring in more help, but you also increase the workload, which has to be done within the same time. So you double the size of the system you solve, you consider twice the number of processors. And here again, it's the 2 supercomputers, and now we go to the degrees of freedom. Recall the domain is a spherical domain of the Earth mantle. So the relative, so approximately, the thickness is 3,000, 10 is missing, kilometers. And if you would like to have a resolution of 1 kilometer, at the end, you need more than 1 billion degrees of freedom in your system, in your algebraic system. And you solve it on these big machines within a couple of minutes. It's just below 3 minutes. That's the solution time to solution of this huge amount of degrees of freedom. So this is a simulation result for the temperature, and, so this one, both are for the temperature, sorry about this. And this is just much, much smaller size. It's just 10 to the power of 9 unknowns, but it's also not worked out on a supercomputer, but on a small mid-sized cluster working at the chair in Erlangen at the computing center there. It's a group of Uli Rüde. So time to solution is what counts on the machine. And you can think, okay, a time to solution, who cares if I have to wait 2 minutes or 3 minutes? Of course, this is an excellent question. And if you go tomorrow afternoon downtown and have an espresso, and if you pay 4 zlotys or 6 zlotys, most likely you don't care. What's the difference? It's not a too big difference for you. But if you go as a young postdoc to Munich and try to find housing, and you have to pay for your home 1 million or 1.5 million, then suddenly this factor of 1.5 can change your life. And this is exactly with the supercomputers as well, because they're extremely expensive. They have extremely high power consumption at all. So even the runtime, what they burn as energy, can go into the 10,000s of euros. So you are really forced to think about twice about the timing. And what we have here is something which shows you that a smart or not such a smart discretization or mathematical model can make a big change. So I told you about the Stokes problem. And I have been discussing in the mathematical formulation where we enter the Laplace operator, a vectorial Laplace operator, bringing in a tensor which is non-symmetric. And the tensor basically has gradient U1, gradient U1, gradient U2, gradient U2, or if you go to the variational formulation with a test function V, and then you have here the third component, but no coupling in between. But whereas you go to the original slide, if you think back, there was not the divergence of the gradient written, but it was the divergence of the stress. And the stress was not defined as the gradient. The stress is a symmetric tensor. So the stress was defined in terms of a pressure component I'm neglecting for the moment, but then in terms of the epsilon, of the strain rate. And the strain rate is just a symmetrized gradient. So no big deal, you might say. But this small, tiny difference is filling up these parts here. So if you implement it in this mathematical way, you gain a factor of 1.543. If you implement it in this physical way, you get a 1.5 in the factor. You lose it. So you have always to think first in what situation you are. And of course you can say, well, if this is a 3 times 3 tensor, which is symmetric, why is it only 1.5 factor more expansive? Because on the main diagonal we have the same entries. So I have just 3 times a scalar. And then I have the 3 off diagonals. Why is it only the factor of 1.5? And this is what we will see on the next slide. This comes from the fact that if you do not compare the factor between these two numbers, but the difference, you see that the difference is pretty much always the same. So why is it so? Because, again, the algorithm costs you time in communication and in flops. And the flops, let alone, this is the plus, the minus, the multiplication operations, they scale perfectly well if you go to the bigger machines. So if we go to the bigger machines or the bigger number of unknowns, then we have a perfect scaling in the computation. But we have no perfect scaling in the communication. And that's the reason why the difference is very much the same, whereas the ratio between these two numbers is going down on the bigger machines. So on the bigger machines, it's getting relatively more easier. So was it the truth what I told you? Well, of course, this equivalence between physical and mathematical Stokes operator is only correct if the viscosity is a constant. If the viscosity is not a constant, this equality between these two operators is not true anymore. So we have to understand what happens in this case. And in this case, I'm skipping the details, but basically the principal ideas goes back to Lyon's. The idea is to introduce a new pressure and to rescale the pressure by the divergence of U. And by doing so, I'm not talking about the mathematical details here, but by doing so, I would like to show you the structure of what we get. By doing so, you go from such a matrix with all the cross-coupling terms to such a matrix. And this matrix, the red and the blue part, this would be the mathematical Stokes operator for piecewise constant viscosity. And it's physically non-correct. This would be the physical Stokes operator, which is correct, no doubt about it, but it's not efficient to implement. And then there's a small possibility to modify the mathematical incorrect system by some additional terms living only on this interface between these two subdomains. And by so you can save this factor 1.5 in the time to solution. Just mathematically, you have to show that it's consistent, that it's stable, this formulation, which is non-trivial in 3D. It's trivial in 2D. Why is it trivial in 2D? Because in 2D, the modification you're doing is 1 over d minus a half, basically. And in 2D, well, the d is 2. So the modification is 0. But in 3D, it's unfortunately not 0. So in 3D, you have to work for it. And what you see, the inconsistent operator, so the mathematical Stokes operator, does not converge at all. There's no convergence, because these missing parts at the interface ruin everything. So what else? One last sketch and one last thoughts to give you for thinking on your way home is, well, now we have these big machines. We can master these big machines. But these big machines have hundreds of processors, 100,000 of processor in it. And it's not so unlikely that one of it is failing, is corrupting, is breaking down. So the idea of a multigrid method, which is an iterative solver, is that you reduce the residual, meaning you get a closer up to the top, and on the top you have an accurate numerical solution. But then one processor is failing, it's crashing down. It might be memory which crashes down. It might be power loss of this processor, whatever. If nothing is done, if you just go on with the rest, well, part by part, the neighboring ones are also falling down. It's really like in a climbing situation without safety going in there. And at the end of the day, you go on, and everything is down back to the checkpointing level. So checkpointing is quite often done if you do long production runs, that from time to time you write back something. But checkpointing is also expensive. So you're back to the beginning. So it's like in a Monopoly game. You have to go back to store, but without getting some money. Okay, what do we need? We need fault-tolerant algorithms, which is a relatively new field. It's really still in its infancy. So there is a series of papers from this year, from last year, and why not hardware-based strategies? Okay, this you can do if you have a laptop, then you put the same laptop next to this one. But this you cannot do if you have a supercomputer. You have not to spare another 100 million euros. So, and software-based strategies might be too slow, because let alone writing down the data of 1 billion degrees of freedom to the memory, to the disk, is taking more time than the whole solution process. So you need an algorithm which can recover by itself. And a typical test scenario would be 1 billion elements, 1 million cores. Each of those can fail. Let us assume that only one fails. What is the idea? Well, as soon as one fails, you fix the connection. You freeze the communication to the other ones. Because if you freeze the communications, the other ones, they are not inflected, they do not get corrupted. They are fixed, they are safe now. And then, well, you have to bring in Superman. What does it mean for a supercomputer, bringing in Superman? Well, just more processors or more powerful one. And this one has to speed up, so the other ones are continuing, and this one has to speed up with more power to catch up with the rest. And then, at the end on the top, at some point you can replace Superman by your standard compute node again, and at the end you reach the top without too much delay. That's the ideal situation. Of course, in practice it's never a perfect life, but first numerical results show you this. So you're falling down from different heights. Here you're already almost on the top. You would like to have an accuracy, which is basically rounding error precision. And here you fall down from a moderate height, but here you're falling down really from very, very high. And now you have to recover this part, and you bring in different strong or weaker Superman, And the good ones can catch up. So the good ones, this is a light green line you can hardly see, but it catches up and reaches basically with the rest of the group the top. Okay, so this is not what I'm talking about. And, whoops, this was one too fast. To summarize and to conclude, well, we have seen that mass balance, which is violated in a strong sense in many numerical schemes, can be recovered by flipping back and forth between meshes, that hierarchical hybrid grids have a perfect lean data structure and are proper for using on supercomputers. And we have this as a relatively new topic, uncertainty. But uncertainty not only in the data, which I didn't speak about, but which is of course as important, but I was addressing only in this sketch uncertainty concerning the reliability of the hardware components in your system. So from tomorrow on, the time for free lunch is over. What does it mean in this context? Well, it's not that you're not getting a lunch voucher for Sunday, but it's the fact that if you cannot solve a problem by now with your software, you can't just wait for the next computer. You're just not buying the next laptop. It will not help you in the future anymore. So you need performance models which are much more sophisticated than just counting the number of flops. So counting the number of flops of an LU decomposition will not really tell you how fast it can be implemented on one of these big machines. And finally, that everything runs smoothly and is efficient at the end of the day, it can be only achieved by a co-design between the different disciplines and groups. And with this, I would like to thank you very much for your attention.